Hi. Today, we're going to implement a linear regression model from scratch. We'll start out with the theory and the equation. Then we'll implement the equation in Python. Then we'll calculate the r-squared value to measure how well our regression fits the data. Let's dive in. In this table, we see data from the Olympics. So each row is a different country, and we have data in each column about each country's entry into the Olympics in a given year. So let's say that we want to use the number of athletes a country entered into the Olympics to predict how many medals they won, which makes sense. The more athletes you enter, generally the more medals you would expect to win. If you only enter one athlete from your country into the Olympics, the most medals you can win is one. And if you enter 100 or 1,000, you can win many, many more medals. The first thing we can do is we can go ahead and plot each row onto an axis, where the y-axis is the number of medals the country got, and the x-axis is how many athletes they entered. Then we'll plot a few extra points that aren't in this table, but are in our larger data set. Then what we can do is draw something called a regression line. And this line indicates the relationship between the number of athletes and the number of medals. And as you can see, the line approximates the shape of our data. You can see that in our data, as the number of athletes goes up, the number of medals also goes up. And the line shows that relationship. And what we can use this line to do is make predictions. Let's say we want to predict how many medals a country will win if it enters 300 athletes. We can use this formula to do so. Y hat equals B0 plus B1x. And Y hat is the predicted number of medals. B0 is the y-intercept of the line. So it's where the line will hit the y-axis. You can't actually see it on this graph, but it'll hit the y-axis a little bit below 0. B1 is the coefficient for athletes, so it's the slope of that regression line. So for every one athlete you enter, how many medals do you expect to win? And then X is just the athlete count, so it's the number of athletes your country has entered into the Olympics. And here's an example of actually making a prediction. So let's say we want to predict how many medals we will win if we enter 300 athletes into the Olympics. So we'll first substitute X for 300. Then we'll add in our coefficients for this line. So the y-intercept is negative 3.7, and the coefficient for X is 0.2. So for every athlete you enter into the Olympics, you expect to win 0.2 medals. So we multiply that out and we end up with our predicted Y of 56.4. So our prediction would be that if we enter 300 athletes into the Olympics, we will get 56.4 medals. And that's based on this regression line that traces the shape of our data. Now you might be wondering, how do we calculate and get these coefficients? So that's the next thing we'll talk about, and what we'll be doing in this video is really working through how we calculate the coefficients and use them to make predictions. So we can actually use this same equation to represent our actual values of y. So you notice we got rid of the hat over the y. So y hat is our predicted values, but just y is our actual y values. And the y is just our medal count. So you can see we can use a very similar equation to represent our actual y values. We just need to add in something called E. So y represents our actual medals, and E is our error. So as you can see, the error is the difference between how many medals our line predicts a country will get and how many medals the country actually got. For example, we can see that the top right is highlighted. So we can work through using that dot as an example. So in that example, 438 athletes were entered into the Olympics. So our X is 438 and our Y was 106. So you can see that we can represent our actual Y value using these coefficients and the E value. So it's just basically calculating the value of for y that we predict using the line, and then adding in the error to get the actual y value. And we can do that for all of the points that we have already plotted. So you can see that we can create similar equations from all of these points. And this is the beginning of calculating our coefficients, is representing all of these individual y values like this in these equations. So we can take those same equations we just saw and turn them into what's called matrix form. So you can see at the left, we've put all our y values into a matrix. So each y value is stacked on top of the other y values. Then we've put our x values and a 1 column into the x matrix. So the 1 column is to enable us to add in the y-intercept, and I'll explain that in just a second. Then we have our b matrix, which includes our coefficient values. So b0, which is the y-intercept, and b1. And then we have our error matrix, which includes all of our error values. So this is just taking the equations we just saw previously and representing them in matrix form. And the reason why this works is because matrix multiplication works differently from regular multiplication. So when we multiply the X matrix by the B matrix, what's actually happening is this. The first thing we do is we start at the first row in X and the first column in B. B only has 1 column, so we only need to work with that 1 column. And then what we do is we multiply the first element in the first row of X times the first element in the first column of B. Then we move on to doing the same with the second element in the first row of X and the second element in the first column of B. And that generates our first equation, which looks the same as the inner part of the equation that you just saw. Then we do the same for the second row and the third row. And finally, we finish with the fourth row. So matrix multiplication is a linear algebra concept. And if you don't know linear algebra, don't worry too much about it. But matrix multiplication is going to enable us to calculate the coefficients for linear regression. So we now have our 4 equations, or the center part of the equations that we've generated with matrix multiplication. And we can represent these in matrix form. And what we end up with is a 4x1 matrix. And that means it has 4 rows and 1 column. So if you solve the equations, you just end up with 1 value. So each row only has a single column. And a trick about matrix multiplication is the first matrix you multiply, you take the number of rows, and the second matrix you multiply, you take the number of columns, and that is your final number of rows and columns. So we take the column count, the row count from X and the column count from B, and that is the final shape of our XB matrix, which is these two multiplied together. Another thing is, in order to multiply 2 matrices, the number of columns in the first matrix you're multiplying has to match the number of rows in the second matrix that you're multiplying. So just keep those concepts in mind, and we will continue with just a little bit of linear algebra that we'll need to actually derive our formula for finding the linear regression coefficients. The reason you would multiply these two is to get this combined XB matrix. Now, one other thing you can do with a matrix is create something called a transpose. And if you look at the left, X with the superscript T is the transpose of X. And the transpose is just X basically turned to the side, turned to the right. So the rows become the columns. And what we end up with is we started with a 4x2 matrix, X, where you have 4 rows and 2 columns, and we end up with a 2x4 matrix, where you have 2 rows and 4 columns. And the nice thing about the transpose of a matrix is that if you multiply the transpose by the original matrix, you end up with a square matrix. And remember that the final product of matrix multiplication takes the number of rows from the first matrix you're multiplying and the number of columns from the second matrix you're multiplying. So this multiplied matrix, X transpose times X, is a 2 by 2 matrix. And it's a square matrix. And what's special about a square matrix is you can invert it. So an inversion of a matrix looks like this. So it's the same size as the original matrix, but it has an interesting property. And that property is that if you multiply the original matrix by its inverse, you end up with something called the identity matrix, which in this case is symbolized by I. So we took the inverse of X transpose times X and we multiplied it by X transpose times X, and we ended up with the identity matrix. So why is the identity matrix special? It's special because if you multiply the identity matrix by any other matrix that's the same size, you end up with the matrix you multiplied it by. So an identity matrix is kind of like multiplying something by 1, right? If you multiply 4 times 1, you end up with 4. If you multiply the identity matrix times another matrix, you just end up with that matrix. The identity matrix cancels out. All right, so we just covered transposing a matrix, finding the inverse of a matrix, and the identity matrix. And these are all concepts that are important when we actually build our linear regression formula, which we will get back to now. So this is the matrix that represents our equations that we just saw a couple minutes ago. This basically shows that our actual y values equal our x values times our coefficients plus our error. We can get rid of the matrices and write this in a simpler format, which just looks like this: y equals xb plus e. And from here, we can actually solve for b, so solve for the coefficients. So the first thing we're going to do to solve for the coefficients is we're going to drop our e matrix because we are trying to minimize our error. So we're going to set our error to 0 in order to minimize it. And now we need to solve for b. So to solve for b, we need to get rid of x, right? We need to be able to say b equals something because b is our coefficient matrix and we want to solve for our coefficients. So in order to do that, in order to cancel a matrix out, you need to multiply it by its inverse to get the identity matrix. But x is not a square matrix, right? X has a different number of rows and columns. So the first thing we do is we multiply x by its transpose. So we multiply both sides by x transpose. And if you'll remember, x transpose times x gives us a square matrix. Then we multiply both sides by the inverse of x transpose times x. And if you'll remember, the inverse of a matrix times that matrix gives you the identity matrix, which is basically treated as just 1. It cancels out. So we'll cancel out the right side and we'll end up with the identity matrix times b equals all the stuff on the left. And then we can cancel out the I, just get rid of the identity matrix. We can treat it like a 1. And then we get our final formula. And I'll flip that formula around and we can see here b equals the inverse of x transpose times x transpose times y. And that is going to solve for our linear regression coefficients. And even though we only showed the example in this short animation of using one variable as a predictor in our x, we're actually going to use this same equation to predict medals given athletes and previous medals, which are 2 columns in our data. So given the number of athletes a country entered into the Olympics and how many medals the country won in the last Olympics, can we predict how many medals they'll win in this Olympics? And we're going to use this formula, b equals the inverse of x transpose x times x transpose times y, to find the coefficients and make our predictions. So the next thing we'll do is go ahead and actually code this in Python. Here we are in Jupyter Lab, which is a way to execute Python and R code and view the results really easily. The first thing we're going to do is we're going to import pandas as PD. So pandas is a Python data analysis library, which is great. We're also going to import numpy as NP. NumPy is a library that lets you work with matrices in Python and do things like get the inverse of a matrix. Then we'll go ahead and read in our data, which is the same data that you just saw earlier in the video. So we'll read in our CSV data and we'll take a look. And there's a few more columns than what you saw before in the video, but the main columns we're going to use are athletes and previous medals. And we're going to use those columns to predict the medals column. And you can see each row is a country's entry into the Olympics in a given year. And we have some data about the athletes, such as their average age and height, that we won't be using, but you can definitely experiment with on your own. So you'll remember the equation from earlier. So we'll go ahead and just set up the parts of that equation. So we'll set up our X matrix, which is going to just be our athletes and previous medals columns. And we'll go ahead and copy that. And then our Y is going to be teams medals dot copy. So that's our X and our Y matrix. So we can take a look at X. So X has our athletes and our previous medals values, and it has 2014 rows because that's how many individual entries into the Olympics we have data for. And we can take a look at our Y matrix, and you can see it's the medal counts for those countries. So how many medals they earned in the Olympics. Now you'll remember we had a column in our X matrix that was just all ones, and that column was so that we could multiply things out and get the Y-intercept. So we're going to add a column to our X matrix called intercept, and we're going to set that to 1. And then we're going to reorder our matrix so that the intercept column comes first, because when we multiply the matrices out, that is our first coefficient. So we'll just reorder our matrix. So you can see our X matrix now. We have our intercept and our athlete count and our previous medals count. All right. Then what we need to do is create our X transpose matrix, which, thanks to the magic of pandas, is just x.t. So let's take a look at this. And we can see this is the transpose of our matrix. The rows have become the columns. Then we can calculate our coefficients. So the first thing we're going to do is we're going to use NumPy to take the inverse of our matrices, xt times x. So this at symbol here, which looks kind of strange, is the matrix multiplication operator in Python. So this is saying take the transpose of x and multiply it by x, and then take the inverse of that whole thing. Then we'll multiply that result by the transpose of x and by y. And as you'll recall from our formula before, this is our formula to calculate the coefficients. So let's run that, and let's take a look at b. And we now have our coefficients. So this is b0, this is b1, and this is b2. So this is our y-intercept, the first coefficient here. The second one is the coefficient for, is that previous medals? For athletes. So for every one athlete you enter into the Olympics, how many medals do you expect to win? And then this is the coefficient for our second variable, which was previous medals. So for every medal you earned in the previous Olympics, how many medals would you expect to win in the current Olympics? So that's what these coefficients are. And then we can just, to make it a little bit clearer, we can go ahead and set the index of our B data frame, pandas data frame, to our X columns. And you can see we've changed 0, 1, and 2 to now the name of the column that it represents, just to make it a little bit clearer. Then we can compute predictions. And you'll remember from the equation y equals xb, our predictions are just our X matrix times our coefficient matrix. So we'll take a look at our predictions. And here they are. We now have 2014 predictions, one for each row. So We did a lot there. We implemented that whole formula in Python in very little code, thanks to pandas and NumPy, which is great. So this is our whole formula implementation. Now, we have these predictions. How do we know if they're good or not? That is the next thing we're going to look at. And I'm going to walk you through a quick animation just to help you understand how we can do that evaluation. All right, let's jump back to our axes from earlier where we plotted each individual data point and we drew our regression line. So that's over on the right. So the difference between each individual point and the regression line is the error. That's the difference between our predicted y and our actual y, because the line is our predicted y and the dots are our actual y values. So what we can calculate is called the sum of squared residuals, which tells us essentially how big our errors are. So that is subtracting our predicted y from our actual y value, squaring it, and then adding them all together. And that gives us something called our sum of squared residuals. We can also calculate something slightly different. So this line that I just drew now symbolizes our mean y value. So it's just the arithmetic mean of our y values. And the difference between our actual y values and the mean y value is shown by these bars here, these purple bars. And what this is called is the sum of squares total. So this is the difference between the y values and the mean y value squared and then added together. And this is a measure of the variance within the data. So the larger this is, the more difference between individual data points and the mean. So the more spread out the data is. And to figure out how good our predictions were, how good our line is at approximating the data, what we can do is calculate something called the R-squared value. So we take our sum of squared residuals, we divide it by our total sum of squares, and then we subtract that from 1. And the bigger the R-squared value, the better our line is fit to the data and the better our ability to make predictions is. So what the R-squared value is in technical terms is how much of the variance in the data set is explained by the X values. So you can imagine in this example, looking at our athlete count and our predicted medals, the country's difference in medals year to year doesn't solely depend on how many athletes they enter, right? It also depends on other factors. So the R-squared value tells us if essentially how good the model we've trained is at making predictions, or if there are other factors out there that our model doesn't know about or didn't take into account. All right, let's go back and actually write the code to calculate our R-squared value. So the first thing we'll do is we'll calculate our sum of squared residuals, which is just y minus our predictions. And we'll square that, and then we'll take the sum. So this is just implementing the formula for SSR that we saw earlier. Then we'll calculate SST, which is y minus y dot mean squared dot sum. All right, so let's look at SSR. So this is the sum of all of our errors between our predicted y values and our actual y values. And then we'll look at SST, which is our basically the amount of variance in our data. Then we can calculate R-squared, which is just 1 minus SSR divided by SST. And let's take a look at R-squared. So our R-squared value is 0.87, which is close to 1, which means that our line is actually good at predicting our data. So that means that we fit a pretty good model because this data is relatively linear. So there's a linear correlation between previous medals and athlete count and the number of medals that you earned. One other thing that we can do just to determine if our model was good is we can use the reference implementation from scikit-learn. So from scikit-learn, which is a Python machine learning library, we can import the linear regression class that they've already written. We can initialize it. And then we can fit that linear regression model to our data. So we'll fit it to our athlete count and our previous medals. So we'll pass in these two columns. And then we will pass in our Y value, our medal column, so it can make predictions on our medals. And then we can take a look at the coefficients that come out of this model. So we can see that's our intercept. And we can see these are our coefficients. And these are the same as the ones we computed earlier, right? So that's our y-intercept, negative 1.96, same as the scikit-learn, what scikit-learn spit out. Our athlete coefficient is 0.07. That's the same as scikit-learn. And our previous medals are 0.73. And that's the same as what scikit-learn said. So why would you want to implement your own linear regression model? A few reasons. One, it helps you understand linear regression better, which makes it easier to know when to apply linear regression and when to not apply linear regression. It doesn't work well for all data problems and all prediction problems. So that's one. Two, it can help you on interviews and help you build a portfolio. So a lot of companies in interviews will ask you about machine learning algorithms and how they work. It can also help you implement custom use cases for linear regression. So if you want to do something that's non-standard, if you understand it and can implement it, you can do something a little bit differently than just the standard implementation. All right. We went through a lot here. We went through linear regression from scratch. We looked at the theory, we found the equation, we implemented it, and we figured out how to evaluate if our model is good or not. So I hope that was a good introduction.